Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Rahul Gupta. Dr. Gupta is an assistant professor at the School of Electrical Engineering and Computer Science at Washington State University. His research focuses on the modeling, operation, and planning of multi-energy systems within distribution networks, addressing various types of uncertainties, measurement, and model-less control schemes, model identification techniques, and synthetic energy system generation. Dr. Gupta earned his BTech degree from NIT Roorkela, India in 2014. He earned his master's and PhD degrees in electrical engineering from Swiss Federal Institute of Technology, Lausanne in 2018 and 2023, respectively. Prior to his current position, he was a postdoctoral researcher at Georgia Institute of Technology from 2023 to 2024, supported by postdoc mobility grant from Swiss National Science Foundation. His doctoral research was awarded the EPFL PhD Thesis Distinction and Electrical Engineering and ABB Award. Dr. Gupta, it's a great honor to have you for today, and the floor is yours.
Thank you. Let me share my screen. Okay, you can see my screen well?
Yes, we can.
Perfect. So yeah, first of all, thank you, Dr. Prakash, for inviting me to this seminar series. And thank you for the introduction. I was not sure that you will read the whole thing, but yeah, thank you. As I said, my name is Rahul Gupta. I'm an assistant professor at the School of Electrical Engineering and Computer Science. And today I'm going to present a topic of research that I do in my lab, which is basically on unlocking EV charging flexibility for dispatching active distribution systems. And we'll talk about theoretical aspects and what are the challenges or the opportunity we have in the real world deployment of these EV flexibility. I know some of the attendees that are in this webinar might be having background of cybersecurity, so I will make sure that I will highlight some cybersecurity aspect of EV charging flexibility. So let me start with this outline. So first, I will talk about the main motivation behind this work. What are the challenges and opportunities with EVs coming in along the years? And I will talk about mainly two use cases. So first, how to tackle the problems that comes by integrating more and more EVs in the power systems and the transport networks. And then I will also talk about another use case, which is, can we use flexibility from the EVs to provide some grid services? And then we'll conclude with an experimental validation on a real microgrid testbed, which is basically validating one of the use cases in this scheme. So let me start with the motivation. So the graph here on the right basically shows how electric vehicle and penetration is going to evolve in different parts of the world. So you can see, depending on where we look, the percentage of vehicles that is going to be electric may range from 50 to 70% in the next 5 years. And this will produce a lot of challenges into the power systems, such as there would be increased electric load for the distribution systems. There could be voltage problems because most of these electric vehicles are interfaced to the distribution system, which is the lowest voltage level of the power system. There's a problem with the transformer congestion, increased uncertainties because these are difficult loads to forecast. However, there is also opportunities in terms of flexibility because these electric vehicles inherently have battery storage systems, which can be used for some form of flexibility. If we look for the US case, here we see on the charts the evolution of EV penetration for the light duty vehicles as well as the medium and heavy duty trucks. And what we see is that there would be around, like if we look by 2024, there was already 5.7 million light duty vehicles on the road, which were electric. And if we see every year, around 10% of the new vehicles are electric. In this case, the California leads the nation in EV registration, accounting for around 35% of the total electric vehicles which are sold, followed by Florida and Texas. And here you can see also on the map. There has been also increase in adoption of medium and heavy duty truck electric vehicles. And this has been possible because of recent decrease in the price of the batteries, as well as the increasing energy density of the battery storage systems, which are integrated into these trucks. And all of these EVs penetration will basically increase the electricity demand significantly, right? We see a lot in the news how much electricity demand is going to come from the data centers. But if you look at the charts, the second largest growth of electricity demand will be from the transportation sector, which is EVs in the next 10 years. So it is substantial. It is something that we cannot ignore. The power system is gonna have to absorb this amount of load from the transportation sectors, and this will cause several challenges. For example, one challenge is to forecast this electric load. It will require some form of control of the EV charging station on large scale, because it will cause uncoordinated charging will lead to transformer congestion, voltage problems, etc. So these charts basically shows that the amount of electric load that is coming from the transportation sector is significant, basically. So now one can question, okay, how can we meet this much of EV penetration in the future? The answer is it depends. So the schematic here basically shows with a different penetration of EVs, what should we do? What should we do to increase the hosting capacity of the power system, which means that how much EVs can be penetrated. So if you look at the red case, where we have very low penetration or low EV adoption, in this case, basically we can manage the EVs without any coordination. So it doesn't affect much the peak load if you have low penetration of EVs, and you can just have uncoordinated EVs in the network. Whereas if you want to increase the EV penetration, you need to basically have a different level of complexity. For example, if you consider these blue case, you might want to coordinate the timing of the charge so that you are shifting the load during the day. If you want to further increase the EV penetration, we will need to control the EV charge in an active way. So basically, you are also modulating how much power EVs are consuming at each time step, and that is unidirectional. If you want to further enhance or the flexibility of EV charge, you'd want to do a bidirectional control of the charging, which means that EVs can provide or feedback the power to the grid when it needs the support. So depending on how we complexify the operation of EVs integration into the power system, we can achieve different level of EV penetration into the system. Let me also briefly talk about the cybersecurity aspect of the EV charging infrastructure, as it's an important aspect. I'm just highlighting one of the report from Sandia National Lab, which basically talks about whether integrating a large amount of EVs may increase more vulnerability into the system with respect to cybersecurity. And cybersecurity is a critical consideration with any high connected infrastructure assets like EVs. And basically, this figure shows an overview of the different components. Like you have metering infrastructure, you have EVs interfaced with underlying communication infrastructure that may be subjected to cyber attacks. And as more and more DERs are also getting interconnected, they are subjected they're communicated through some kind of a centralized communication link, so they may be subjected to some form of cyber attacks. And given that we have a large amount of EVs penetration in future, and if they are operated by 1 or 2 or 3 vendors, assuming that they are using similar communication protocol, there could be a large scale cyber attacks that may affect in the power system in some way. The report also highlights this risk matrix. So here on the y-axis, you see the threats and vulnerabilities, whereas on the x-axis, you see what are the consequences that can happen on the power system. So you see these consequences from low to medium to high to extreme cases. In the high cases, you basically have lower level of power system impacts, basically regional outages, which can be limited to distribution systems. In the major cases, like extreme cases, you can have a transmission level blackout or even several outages over extended period or extended region. The report also highlights that there were no such attacks were found as of now. And this is because the EV penetration is not that high at that moment. But it might be in the future that this will become significant problem if it is not managed well, basically. Here I'm also showing you an example of a real microgrid network, which is situated on EPFL campus in Switzerland. And this contains several controllable resources, such as battery storage, photovoltaics, EV charging stations. And I will come back to this figure when we do experimental validation. Basically, what I want to show here is that they are connected through communication networks in a centralized way. So this is basically hosted on a computer, and we are talking to all these controllers through some communication layer. And also we have metering device, which is also sending data. So there could be attack in any of these communication channels, which might affect our control system. And if it is not managed well, if there is no such mechanism in place, then this will affect the power system, basically. There are also a lot of research opportunities for the integration of AI and data-driven based tools for EVs and power systems, such as predictive EV demand per plug, which is a complex task if you come down to the plug level, because there are several variables which comes into the place. For example, human behavior, influence of transport and power systems, diversities in EVs and plug types, charging modes, etc. A lot of people are also researching on data-driven reinforcement learning for the system where you don't have enough information. For example, let's say you don't know about the power system and you still want to achieve some kind of control which helps the power system. There are people working on surrogate models of EVs that can be used in the grid control problems for speeding up. And in terms of cyber attacks, there are people working on attack detections. So coming back to the main topic of this talk. So in this talk, I'm going to focus on presenting you 2 different control schemes, which is using EVs for providing grid flexibility, as well as tackling some grid problems such as minimizing the voltage imbalance. And then we'll end with the experimental validation for one of these schemes. So these are basically coming from 2 different papers, which are referred here. And if you want more detail on these aspects on the theory, please, I suggest you to read these papers. So let me first go through the first topic, which is doing the grid-aware EV control for tackling voltage imbalance. And the problem here is that most of the EVs chargers, especially the residential ones, are of single-phase type. And if they are not coordinated well, it can cause some form of voltage imbalance in the distribution system. And voltage imbalance, for the people who are not used to power system, is basically our power grid is three phase. Each phase should have similar voltage magnitudes. And if the voltage magnitude of one of the phase is way far from the other ones, then basically this is voltage imbalance. And there is standards in IEEE that you should respect within certain percentage. So every distribution system operator should make sure that the voltage imbalance metric is not above that threshold. So coming back to electric vehicles, impact on the distribution systems. So EVs, the power demand may range from 10 kilowatts to even 500 kilowatts. And so if you have a lot of EVs, it has high power demand. It has likeliness to violate the network constraints if they are not installed in like taking all this consideration of whether it can violate the transformer flows or branch currents or under voltage, etc. Also, the EV plugs can be of different types, so single phase, three phase, DC. And if there is a high penetration of single phase chargers, which is basically residential chargers, there will be increase in the voltage unbalances. And this is also referred to as power quality deterioration. So if you have a lot of voltage imbalance into the system, you have low power quality into the distribution system. So the problem setup that we consider is that grid is connected with several EV aggregators. An EV aggregator may be EV charging stations, which are hosting several EVs that are coming to the charging station, plugging their EVs, and they want to meet their SOC requirement. They want to leave at a particular departure time, etc. And we want to develop a power allocation algorithm on the grid side, which accounts for these EV user needs, as well as grid operational and power quality constraints. And it's stochastic in nature in a sense that the grid could be interfaced with other resources which are stochastic in nature. For example, renewable resources, right? They have some uncertainty in the generation because that depends on the weather. If you have solar plant, load might have uncertainties. So the grid problem can be formulated in a stochastic problem, which models the grid as well as the grid constraints. Whereas EVs aggregator, the main objective of EVs is to satisfy the EV user demand, which is coming to the EV charging station, and also consider the constraint of the EVs and EV charging station, right? And so EVs can be formulated as a deterministic problem. This whole thing, if you want to solve in one simple or single optimization problem, this becomes huge because you have to take into account of each of the EVs user needs, which might be thousands of EVs connected to the one distribution system. And you cannot also expect that the grid operator knows particular details about EVs, power capacities, energy capacities, at what time they came to the charging station, and at what time they left from the charging station, what is their SOC target, etc. So in this way, the problem that we formulate is in a distributed way, which means that the grid operator can solve their own problem, allocates the power or power envelope that EV aggregator needs to satisfy, and they operate within this region, and they communicate this through some communication channel. We'll talk more about this. So let me talk about briefly how the grid operator problem looks like. So it is formulated as a stochastic optimization problem, which the objective is wants to keep the grid feasible while considering the uncertainties on the injections. So grid feasible means that the voltage and the line flows should be within the limits. So here is an overview of how the grid problem looks like. So you have a set of inputs. You have inputs basically is the scenarios of the nodal injections, which is modeling the uncertainties. You have the inputs from the grid, which is the parameters of the network. The objective here could be anything like, for example, minimizing losses. Here we consider minimizing branch current flows, which is coming from reactive power. The constraint is basically we want to keep the voltage within the bounds. You want to keep the branch flows within the bounds, and you have power quality limits as well. And the output is basically what should be the power allocated for each EV aggregator. If you look at the inputs, basically we want to consider the stochastic model of the non-EV injections, such as loads and PV plants. And these are sampled from the pre-computed probability distribution functions, PDFs. And the PDFs can be obtained or estimated from historical data set. So here what we do, that we have a historical data set for, let's say, 2-3 years. We cluster them into different data types. And for each of these subcluster, we fit a multivariate Gaussian mixture model, considering the time correlation, and then we sample it from that PDF to use it in the optimization problem. The other parameter that we have is the grid parameter, which is the resistance, reactance, capacitance, etc. And also we know where the resources are placed. The objective here, could we minimize losses? Here we are just penalizing the reactive power use, not penalizing the active power, just keeping the branch currents within the limits. The constraint that we have is the three-phase voltages should be within the limits. So this constraint basically ensures that the voltage that we have is, let's say, beta could be like 5% of the nominal value. Then we have a constraint on the branch current. So the branch current should be within the maximum limits. And this is the transformer flows should be within the maximum limits. Then we have a power quality constraint, which is basically tells us that the negative and zero sequence voltages are within some percentage of the positive sequence voltages. And these are usually enforced by some IEEE and IEC standards. So basically we take that constraint into the account. Having these as a constraint is nonlinear and non-convex in nature if you look from a mathematics point of view, and it's difficult to solve. So we do some form of linearization. Here we use some kind of first order Taylor approximation, which ensures that your system is a linear program and easier to solve. Yeah. So I'm not going into detail, but basically what I'm saying is that you can express all these constraints that we have in a linearized way. And the output of the problem would be basically these PEVs and QEVs, which are the decision variables. Okay. So at each time step, we would get what is the power active and reactive power set points. That should be enforced by the EV aggregator. So if one particular EV aggregator has, let's say, 10 EVs connected to their charging station, they would ensure that all the EVs together doesn't exceed this power consumption basically in total. And so this is ensured by EV problem, right? So we will talk about now EV aggregator problem. So EV aggregator problem is a deterministic optimization scheme where the objective is to satisfy the EV user needs. That is the target SOC at a specified departure time. The inputs here basically is the data on the that is coming from the EV user. So let's say EV has certain car and it provides what is the maximum charge power capacity, what is the battery capacity and the charging efficiency, right? And this has to be inputted by the user or through an application. Then it also provides knowledge on what is the initial SOC charge, initial SOC of the battery, and what is the specified departure time, or what is the time, what is the SOC that the car would wants to stop charging. And so these are information that should be provided. And then we also have some flags which says that either the EV have reached the SOC target or unplugged, and these are taken into the constraint. The objective that we have is that we fairly achieve target SOC. So if you have several EVs connected into charging station, we would want to ensure that their charging is fair among each other. You would want to give one EV is like 200 kilowatts and other one 10 kilowatts. So you would like to fairly allocate the amount of charge that we are giving to each EVs. And this is ensured by these objectives. So basically, you want to achieve the SOC target, and these are weighted weighted with these kappa. And kappa basically tells us whether EVs have achieved the SOC target or they are in process of achieving the SOC targets, and these are modulated based on which car has how much time left to reach certain SOC, or if the car has a very less amount of time left, then this K will penalize less to that car because you want to reach certain SOC, and it will also favor the cars which requires more energy demand to reach certain SOC target. And so these are some weight factors that are computed appropriately to enable that. If there are questions, I can go through this later on. We also want to minimize the battery wearing, which means that you wouldn't want the power of the battery in the EVs to change very frequently, because that affects the aging of the battery storage, and also the EV user wouldn't like it. So this is enforced by these factors, lambda, and lambda is basically takes into account the history ramping. So it accounts whether if there is a lot of variation that has already happened in the previous time steps, it will penalize more to not do further ramping of the battery. So you don't change the set points a lot. You keep it as constant as possible. The constants that we have here are as follows. So EVs could have or EV and EV plugs could be of different types. So it could be single phase, three phase, and DC. So you need to take into account these as a constant. Then we have a different power limitations on the charging stations or charging configurations, and they are given also by the consumer or the EV user. Then we have a state of charge dynamics. So there could be two cases here. Some EVs, they send back the SOC, real-time SOC directly, and you don't need to estimate them. In other EVs, you probably won't have information from a state of charge, and so you will have to do some Coulomb counting. So the time you start, you basically start also updating your state of charge computation on your side. In this way, you can estimate the state of charge. And then the final one is to linking to the grid subproblem. So if you remember, the grid subproblem gives us this power of EVs in active and reactive power, and we want to make sure that there is a equality holds here, that it doesn't exceed the power allocated from the grid side. So if you want to look the overall problem, this is how it looks like. So you have a grid operator problem, and then you have several EV aggregators, right? In one of the grid, you can have several EV charging stations, and each one can be operated by different player, and their objective are basically to meet user demand, and they're coupled by this constraint, right? So solving in a centralized way makes it bulky, and that's why we go for a distributed formulation. The centralized scheme is not scalable because there's a lot of variables from the EV specific constraints, and it requires sensitive EV user information, right? So we go for a distributed scheme, and this is possible because of linearized constraint. And so we introduce a auxiliary variable, which is basically exchanged at the interface of the EV aggregator and the grid problem. And here the algorithm shows this how it is solved. So you first solve the several EV aggregator problems. So this is solved by EVs aggregated by themselves, and it can be done in parallel because they are decoupled. So if there are 5 EVs aggregator, each of them can solve their own subproblem, which is maximizing their EV user satisfaction, and each of them, after solving their set point, can send it to the grid aggregator, and then the grid evaluates that and gives its own set point, and this goes on till there is convergence. And convergence basically is that both agrees with their set points, subject to some threshold that has been set beforehand. So we validate this first through simulation. So we compare the performance of these 3 different EV controllers to benchmark the proposed one. And we do this for a summer weekday with a time resolution of 5 minutes. And this is used for basically scenario generation. So the first thing is the proposed scheme, which is grid-aware distributed control. Then the two benchmarks algorithm that we compare with is when we don't account of the grid constraint. So this is referred to as here as GULC. So you locally solve the aggregated problem, and whatever EVs aggregated compute, they implement that. Then third one is even simplified one, which is myopic maximum power controller. So charge the EVs at the maximum power until it reaches desired SOC, or unplugging if EVs is unplugged before reaching the target SOC. So this is the flow chart of the comparison. So we start with the PDF of the non-EV injections and the EV user data, which is providing all these EV parameters. And then all these three goes to three different algorithms. And then we have, again, sampling non-EV injections. And then we do some kind of Monte Carlo here, which is evaluating different scenarios of non-EV injections to see if we have some voltage violations, branch current violation, or power quality violations. And then we report this PDF of the grid variables and the EV battery SOC evolution. So the grid setup that we considered is shown here. So we consider this network, which has different amount of loads, photovoltaics, as well as EV charging stations connected to it. And these are the PDFs or the scenarios for the loads and the photovoltaics. These are coming from real measurements. So we used it to learn the PDFs for different data types, and then we sample it when we are creating the scenarios. This is the EV simulated environment, which basically consists of different charging modes. So you see single phase, three phase, DC, etc. You have different car model, such as Jaguar, Tesla, etc. Different power, energy, efficiencies. They are connected at different nodes into the network. It are of different categories: home, roadside, work, and different capacity also of the charging station, etc. So here are the simulation results. So one on the top left basically shows the probability of going the voltage magnitude above the maximum allowed voltage, and also probability of going voltage below the minimum voltage allowed. So what we see here is the green, which is the grid aware algorithm, has the lowest probability among these three, whereas the one which is grid unaware and the myopic controller leads to a lot of voltage violations. And this is mostly during the night time. This is when most of the EVs plug in when they come back from work at home. Similarly, we also see violations for the transformer flows. So we see that during the same time, we have a lot of violations for the grid unaware and myopic controllers, and then also for the branch currents. We also compare the power quality. So here it shows the probability of zero sequence voltage going above the allowed threshold percentage. And here we see that the grid aware algorithm is close to zero, the probability of violating, whereas the grid unaware algorithm myopic controller have poor performance also for the negative sequence. So positive and negative sequence basically tells you how far you are from the nominal voltage, one of the voltage of the three phase, and it basically shows that there is a lot of voltage imbalance going on when you don't consider the network constraint. So that was those were the results from the grid perspective. Now we want to see whether in all of these three algorithms the EV user is satisfied, and this we observe by looking at the difference between the desired state of charge at the departure and the actual ones. And what we see here is that if we have myopic controller, we mostly see the distribution close to zero, which means that there is not much difference between whatever the SOC that EVs wanted to achieve and what they achieve. Whereas for the grid aware control, we see that there is some difference. So EV user may be a bit unsatisfied in the grid aware control because there's a grid violation basically. So to avoid that. Right. So that was the first topic, which was more on coordinating EVs for mitigating problems in the networks. I'm switching to the second subtopic, which is, can we use the local EV flexibility to solve system level issues such as satisfy grid constraint that we show, and also demonstrate for providing some kind of services to the network. So for this, we consider this setup, which is we want to show whether we can use EV flexibility for dispatching active distribution systems. And this consists of two stages, which is the first stage is the day-ahead stage, and the second stage is the real-time stage. This is reflecting how our electricity market works. So in the day-ahead stage, there is the electricity market, which is concluded around 12 p.m., which is basically gives us a profile of the generators that should be followed during the real time. And in real-time operation, since the forecast may be wrong, you need to balance somehow by local resources or resources that you have reserved, and that is called balancing operation. So we want to see whether we can use EV flexibility for such balancing in real time, especially for distribution systems. So first thing first challenge that you have in this scheme is that during day ahead, you want to account for the uncertainties of the EV charging stations, right? Which is difficult to predict because on a distribution level, you have a lot of uncertainties. They are not smoothened out from the EV charging stations. So you need a good amount of historical data from the EV charging stations to predict well the EV behavior. So we come up with this approach where we have a lot of historical data. Then we have this day type selection. So you will see a different behavior of EV charging based on whether it's a weekday or it's a weekend. And then we come up with these three different GMM models, Gaussian mixture models. We select the best ones depending on these metrics that we decide. And then we do some clustering, and as an output, we get these scenarios, which is basically the number of EV charging sessions per day, the arrival and departure times, the initial and final SOC, the battery capacities, and the minimum maximum active power injections imposed by EVCS. So once we have this, then we can basically use that to generate the EV scenario. So for historical data, we have real installation. This is back in Switzerland, where I was a postdoc and PhD. And basically, we had these two charging stations, and this gives us real-time data. And we had these data for over the period of 1 year that we used to train the GMM models. So having that, we basically, this is how the scenario looked like. So we convert from this EV historical data to the power demand. And this shows different scenarios that we may see across the day. So this is for a residential EV charging station, and this is for fast charging station. So the difference is just the magnitude and the frequency of the EVs that are connected to the charging station. We also need to forecast the scenarios for the load and the photovoltaics, and here also we use some form of Gaussian mixture models. And yeah, here basically you disaggregate the actual loads. So you might have a combined measurements where you have behind the meter photovoltaics, and you have to separate which part is the photovoltaic and which part is the load. And so you have to do this disaggregation, and then we train for each of these Gaussian mixture model. And then once we have these PDF or probability distributions function estimated, then we use it to sample the day ahead scenario. So once we have this scenario, so the day ahead problem is basically formulated as a stochastic scenario-based optimization problem, where omega is basically representing different scenarios, and we want to get this S dispatch plan. So you want to merge all the scenario into one single profile thanks to the controllability that can be provided from the controllable resources. And the controllable resources that we considered here are EVs and the battery energy storage systems. So this is the objective, and the constraint that we have is the grid constraints, the currents, the voltages, the power flow equations, the constraint on the reactive power, and then we have EVs and the batteries constraint. The EVs model is similar as before, where we have the objective to fairly achieve target SOC, the constraint on the power level and the SOC level, and the output is the per plug set point. And the battery model is basically the battery parameters. You want to minimize the battery wearing. The constraint is on the SOC again, the power and energy constraint, and the output is the battery active power, basically. Then we go to the real-time operation, and real-time operation, it is formulated as a MPC, model predictive control, which is trying to track the day-ahead dispatch plan. So let's say you are at this period. So usually these set points for 15 minutes, and the real time you want to track this at a faster time scale. So for each time step, you compute this set point. Let's say you divide this 15 minutes into each 30 seconds. Okay. So for each 30 seconds, you are controlling your EV and the battery energy storage systems. And this is formulated as MPC, which accounts that overall, when you reach at the end of 15 minutes, you are able to match the average that you get over the 15 minutes to the actual dispatch plan that was decided the day ahead. And so the MPC fits here. So the problem looks quite similar, but it is the objective that you want to consider is to minimize the resource operation cost. So you have a different operation cost depending on the EV's model and the battery storage model. And then we also want to dispatch, minimize the tracking error of the dispatch plan. The constraint we have is the power balance constraint. We have the engineering constraint again, which is voltage and currents. And then you have a model of the power flow equations, EVs, and the battery energy storage system. So now I'm going to the experimental setup. So this is, we experimentally validate, this is back in EPFL in Switzerland, where we have set of controllable resources. So battery energy storage systems, EV charging stations. One is a fast charging station. One is a small single level or level 1 charging station. And we have several photovoltaic plants also that we were also controlling. And the battery storage capacities are given here, and the EV charging stations capacities are given as follows. And basically, whenever EVs comes in, they have to provide certain data. So this is how the EV's plugs look like, which can be of different types. So in this specific case, the EV charging station has, I think, 5 plugs, and each of them has different capacities. So whenever a EV user enters, it inputs the SOC target that they want to achieve when they leave. Their SOC target may be impractical because sometimes the EV user not aware how much SOC you can achieve in a certain given time. They also specify departure time. They specify whether they are willing to provide for or control their charge for flexibility, and they also provide initial SOC. So here I'm presenting a slide on EV controllability. So one might think that if you want to control EV, it's easy, but it is not. When you do experiments, you see that it takes some time to ramp up and ramp down, and that you should take into account when you're doing these kind of control schemes. And the EV charger also have different modes, like they may take input as a current set point instead of power. So you need to adapt your control scheme based on that. So here are some examples. Also, they have a different plug types, have different protocols. So here I'm just listing these 3 different types and their summary. So if there are questions on this, I can go over it later on. Also, we had to set up this communication framework, which is coordinating the whole operation of getting the measurements from the EVs, getting the measurements from the grid, which is coming from PMUs in this case, getting measurements from the weather. So in this case, we had photovoltaic, so we need weather measurements in form of irradiance. These are all going to our database, right, which can be used for a historical database. Then it's also going to our real-time state estimator, and which is running here in this dashboard. Then all of these goes to the day-ahead dispatcher, which is first forecasting the day ahead as also computing the day ahead profile. And then we have a dedicated workstation, which is doing the real time. So real-time MPC gets inputs from the grid, gets inputs from the EVCS, and once it is solved, then it sends set points to the battery actuator as well as the charging station. And this all happens like within few seconds, less than a second, I would say. So let me go back to the experimental results. So in the day ahead, as I showed before, that we had to forecast the day ahead scenarios. So these are the day ahead scenarios, okay? And the output is this dispatch plan, okay? So we achieve from this profile to this profile, and this is possible because there are differences between this and this is provided by the controllable resources, which is EV charging station as well as battery energy storage system. And with this control, we show that the uncertainty that is there on the profile, on the power profile, is reduced by a lot. So this is the uncertainty when you allow the EV and the battery control. This range of uncertainty accumulates when you only allow battery control but not EVCS, and this is when you don't have any control. Okay, so basically you have balancing error is more than 10 times if you don't have any coordinated charging or no flexibility from EVCS. So that was day ahead. So what we want is that during real time, the dispatch plan that is decided to be tracked, right? So here I show the realized one when you don't have any control, realized with control. So you're controlling the injections from the EV charging station. And these are the power injections from the EVCS, okay? And these are the EV SOC and SOC target that is being achieved for different charging stations. And then we have injections from the battery. So we see that most of it is provided by the battery storage, but also there is some flexibility from EV charging stations. And this is the PV production. So it was a cloudy day, so there is also some uncertainty on the photovoltaics. We also did this experiment for several days to see whether it sustains, not just one off day. So these experiments were done for 4 continuous days, and we see that you're able to keep tracking the dispatch plan over multiple days by controlling EV charging stations as well as the battery storage system. Yeah, I think that was the last slide. Okay, so let me conclude. So EVs, although they are causing issues in terms of increased demand, causing uncertainties or power quality issues, if coordinated well, they can be used to provide grid flexibility. The problems that is of interest to many people is in tackling the cybersecurity issues, which affects the electric grid. And I would again highlight the report from Sandia National Lab, which basically shows can EV-driven cyber attacks can cause instability in power systems, can it lead to cascading outages, and there are several scope for AI and data-driven applications for EV control, attack detection, etc. So thanks for listening. I hope this presentation was useful in some way, and let me for any questions. Yeah.
Thank you. Thank you, Dr. Rahul. Let's open up questions so folks can either turn on your audio and ask questions, or you want to put the question in the chat. Who wants to go first?
Yeah, hi. Maybe I'll go.
Oh, yes.
Yeah. I'm here. I changed to my laptop. So thank you for your presentation. It's very good. And actually, I have some experience doing like economic dispatch and doing similar work. And I think it's
Right.
really interesting. So I have one question is about your like for your first topic, and you talk about the EV aggregator. And like consider the communication topology of different EV aggregator, and so I have a little bit lost in your ADMM, and so how do you design your communication like for each aggregator?
Yeah, so here we consider that EV aggregator have a direct communication link to the centralized controller, the grid controller, and they are talking with each other. Like each of the EV aggregator have direct access.
Oh, so
Yeah, so
I
they're
think
they're,
you
they're
mentioned
linked.
about you want to do something like the distributed. So we still have a central controller. So
This is not. It's kind of distributed because you have. So let me go to the architecture there. All right. Yeah, this one.
yeah.
So basically, the distributed in a sense that these EVs aggregator, they are parallelized. Okay, so each
Hmm.
of them can solve their own individual problem by themselves,
Hmm.
and then send all these set points to one grid operator problem, and then it re-evaluates and send it back to or broadcast to all these EV aggregator, and then they compete again. So they do this till they converge to a certain set point. Yeah.
Okay, okay. Thank you. So thank you for your answer. And I have another question. It's
Yeah.
about
Go ahead.
yeah. So I saw you have three controllers. One is grid aware, it's grid unaware, and another one is myopic.
Right.
So yeah, from our I think based on our experience, and if you're using myopic, and to my understanding, and you may want to use some like the game theory, because each a aggregator they do not cooperate with each other. So I mean that what do you mean the myopic here, and what's the difference between
Yeah.
this
Yeah.
one
So the
and
myopic and the grid unaware were just introduced to show that if you do that, then you have a problem in the network. So what we propose is this grid aware, right? And so we
yeah.
want to see how this is beneficial compared to other two methods.
Oh,
Yeah, so myopic is the one when you have most problems because there is no coordination between the different chargers, and if they are all charging at
okay,
the maximum power, then you have a problem.
okay,
Yeah,
okay. Thank you.
yeah.
Okay.
Uh, any other questions? Anybody else wants to jump in and ask a question? If not, I'll start. On your, how sensitive are your results to the accuracy of those PDF that you talked about? Is your
Mhm.
framework, you know, how sensitive to bias data distribution? Do you see any bias modeling in your thing, or is something that's not done?
So one thing we do is like you have these PDFs, right, that you do based on the historical data. You also validate them by having new measurements. So you basically use, let's say, 60% of the historical data to learn the PDF and test on rest 40%, right? So unless we have good um, enough PDF which satisfies this, then only we proceed with that. And we have seen that the more clustering or sub-clustering that you do, like for example, you have a different charging behavior during the Sunday or Saturday compared to weekday, right? And that should be taken into account. So you have to cluster your historical data based on day types, based on seasons as well, because it changes as per the season, and also different charging types.
Oh, um,
I
yeah.
see there is a one question from Leslie.
Yes, okay.
Yeah.
In distributed systems like Kubernetes, we often see a gap between declared demand and actual usage. How would your framework handle cases where EV users overstate urgency, such as declaring early departure times? Is there any mechanism that discourages the self?
This happens actually. You will see that EV user just say 20 minutes they want to reach 100% SOC. And I mean, you take those into account, but you have also your own mechanism of measuring SOC and estimating SOC. Okay. Um, so based on that, you are trying to make it fair. So we have these fair objectives that that should be considered into the problem.
Yeah, sometimes they exit early, that may affect the estimation. Yeah. How significant is the impact of the charger ramping and set point issues that you mentioned on the charging energy output?
Charger ramping. So the ramping is basically affecting the battery that is in the EVs. And although I don't know, some EV owners, they are aware that if you change your set point a lot, that will cause to the battery wearing. But many EV users are not aware. So yeah, like, but like when you're developing this controller, like as someone who knows about like ramping can affect aging of the batteries, you'd want to have these considered into the objective. So because of that, we have this objective into the EV aggregated problem that you want to minimize the ramping. Yeah, so this is a real issue with the battery energy storage. You don't want to do a lot of ramping.
Did you see any latency issue during that affects the convergence? Maybe I summarize the last question in that context.
Yeah, we do have latency issues, like especially when you do the real experiments, and we have a fallback strategy for that. So if you have some latency problem, you use the previous set point. Like if you don't converge within that time frame. Yeah.
Okay.
So this kind of fallback strategy we basically use, yeah.
How are you using synthetic data to stress test your grid-aware scheduling before it ever implement a real distribution network?
Right. So we do a lot of simulation beforehand with different scenarios. So since we have PDFs already, we generate like thousands of scenarios and run through the system. We also introduce scenarios when we lose communication. So what happens if you disconnect your the EVs like out of communication? Like basically you mimic that. Okay, you don't receive the set point. What do you do in that case? So this scenario we create beforehand and see if the algorithm works. There is nothing unusual happens. Yeah.
Cool. Sounds good. Any other last questions? I have 1 minute. Any other questions from anybody? Are you thinking about this OCPP communication framework for EVs? Are you bringing into your
So
work?
here it was DCMS. I don't know if you've heard of that. You're using that. Yeah.
Okay.
Yeah.
Sounds good. Well, thank you, Dr. Rahul, for your time this morning with us. I appreciate for being here and doing this webinar for us. I think it's a great honor. You will receive a nice plaque from UND and a letter from our dean. Appreciated your time, and hopefully we can work together and
Yeah.
proposals and get something ongoing. Appreciate it.
Yeah, thanks a lot for this invitation, and I hope it was useful for the audiences and like getting some background on this topic. And yeah, thanks for the invitation.
Thank you.
Thank you.
Okay,
Bye
bye.
bye.